All right, y'all, get excited. We are jumping into our next unit, which is all about momentum. All right, so today we're going to start talking about momentum, defining momentum, and then introducing you into something called impulse. All right, so before we start all of that, we do need to know what momentum is. All right, so momentum is just the quantity of motion. All right, so it's the quantity of motion of an object that is moving, obviously. All right, so it is defined by the product. So we have a product. That means that we are multiplying of the mass and velocity of an object. So that's where we get our equation for momentum. All right, notice that we have the symbol for momentum is that lowercase p. All right, why is it an M, you say? Why isn't it anything besides a lowercase p? All right, well, if you remember chemistry last year, then you remember that the uppercase M stands for molarity. That was whenever we were looking at concentrations of different solutions. All right, and then a lowercase m is obviously right here, and that's going to be mass. All right, so whenever scientists were trying to figure out, hey, what is a good letter that we can use to identify momentum, P came up. All right, so they couldn't use uppercase P because uppercase P is power. So they chose a lowercase p. And that was chosen mainly because both uppercase and lowercase m's were already taken. But it also comes from the Latin word patera. All right, so scientists like Galileo and Descartes, all right, they used this Latin word patera to describe the amount of motion. That's what it means. All right, so since we are talking about the quantity of motion and patera means the amount of motion, all right, that's where that lowercase p comes from. Now, because it is measured in mass times velocity, our units, unfortunately, they are a derived unit, but even newtons, joules, and watts were all derived units, but they had just this simple one-letter unit. That's not the case for momentum. All right, so because it is mass times velocity, mass is measured in kilograms, velocity is measured in meters per second. So our unit for momentum is a kilogram meter per second. A kilogram meter per second. All right, so this thing, I don't know why it did this on the bottom. It should be right in your notes. All right, but momentum is a vector quantity, which means that it does have to have a direction. All right, and even whenever we were looking at Newton's second law, F net is equal to mass times acceleration. All right, we know that mass cannot have a direction. Mass can never be negative. It's a scalar quantity. So the direction for our net force came from our acceleration. Well, it's the same thing for momentum. So we know that momentum is equal to mass times velocity. Well, again, mass is never going to have a direction. So if we need a direction for momentum, it's always going to come from the vector quantity of our velocity. All right, so both of those have to have the same direction. All right, now I want you to think about it numerically. Okay, so we have seen another equation that has these two variables in it. All right, mass and velocity. We saw it in our last unit with kinetic energy. All right, so we know that kinetic energy is 1/2 mv squared. All right, so we're using the same variables, but we have very different equations. So we saw how kinetic energy depended more on velocity because velocity was being squared while mass was being halved. All right, but for momentum, it equals just as, or it depends just as much on mass as it does on velocity. All right, so if we increase the mass, that's going to increase the momentum. If we increase the velocity, that's going to increase the momentum. All right, and that's what we see. And that's what we see right here. All right, so we see that as mass increases, so does momentum, and as velocity increases, so does momentum. All right, so momentum has that direct relationship with both mass and velocity. All right, but we cannot forget about the direction with that velocity. All right, now look at these two things. So we have a Mack truck and a McCall on roller skates. All right, so if they're both moving, that means that both of them have momentum. That's great. All right, well, what if both of them are traveling down the street at the same speed? Are they going to have the same momentum? Absolutely not. All right, so the Mack truck will 100% have a greater momentum because it has so much more mass. All right, but what if that Mack truck comes to a stop and the McCall keeps going? Who will have a greater momentum then? Hopefully, you're saying the McCall will have a greater momentum. It does not matter how much mass that Mack truck would have. If its velocity is 0, it has absolutely no momentum whatsoever. All right, so even though the McCall's momentum might be a lot smaller than the Mack trucks, all right, it still has more because that Mack truck would be stopped. Okay. Now this one, oh my goodness, I want you to put big highlighters around this one. This one is super important. All right. A lot of people use the terms momentum and inertia interchangeably. All right. And that is incorrect. They are not the same thing. All right, if you remember correctly, whenever we were talking about Newton's laws, Newton's first law is also called the law of inertia. And if you remember, Newton's first law states that an object at rest will remain at rest and an object in motion will remain in motion unless acted upon by an outside unbalanced force. All right, so if an object is standing still, it still has inertia. It is going to resist that change in motion. It wants to stay still. All right, so it will resist a change in that motion. All right, so even if you are standing still, you still have inertia. However, you do not have momentum. All right, now think of it in a different way. All right, we're getting ready to work on these race cars. All right, and we kind of brought something up the other day. So if you were driving in your car and you let off the gas, does your car automatically just come to a complete stop right at that exact moment? No, it doesn't. All right, it keeps moving and moving and moving until it eventually slows down thanks to friction. All right, well, is that momentum or is that inertia? All right, and the answer is that's inertia, All right, so remember, inertia is an object's tendency to want to continue moving. All right, so that car keeps going due to inertia. Now, does it have momentum? Yes, absolutely, because it's moving. But it keeps moving because of inertia. All right, so just keep that in mind. You can have inertia if you are standing still, but you cannot have momentum. So inertia and momentum are not the same thing. All right, so practice problems. Oh, I meant to take this off of this, so sorry, just disregard. That answer is not the full answer anyway, so we'll still keep going. All right, so we have a 2,250 kilogram pickup truck that has a velocity of 25 meters per second to the east. What is the momentum of the truck? All right, so I'm looking for the momentum. So that lowercase p is my unknown. My first given is my mass of 2,250 kilograms. My second given is the truck's velocity, so 25 meters per second to the east. All right, well, I know that momentum is equal to mass times velocity. So we have 2250 times 25. That does give us 56,250. Beat that. All right, not just 56,000. All right, so 56,250. Our unit for this is kilograms meters per second. And you have to remember that momentum is a vector quantity. It's always going to take the same direction as the velocity. All right, so our velocity's direction was east, so I would love it if you put east for the direction for that. But because this is one-dimensional, if you put a plus at the beginning of it, that is perfectly fine as well. All right, that is perfectly acceptable. All right, now let's look at this. So we have a 21 kilogram child on a 5.9 kilogram bike that's riding with a velocity of 4.5 meters per second to the northwest. All right, I'm looking for three things here. The first thing that I'm looking for is what is the total momentum of the child and the bike together. All right, well, if we're looking for the total momentum, we need the total mass. All right, so to find the total mass, we're going to have to add the mass of the child and the mass of the bike. And then we know that the child and the bike are acting as one, so their velocity is the same. All right, so we're going to have that 21 plus 5.9 times 4.5. That's going to be 26.9 times 4.5. That's going to give us a total momentum of 121.05 kilogram meters per second. Now, this is going to the northwest. All right, we cannot put just a plus or a minus here, all right, because north is plus, west is negative, right? So we have to just put northwest here. Okay, so easy peasy. The second thing that I want you to find is just the individual momentum of the child. All right, so if I'm looking for the momentum of the child, that's going to be the child's mass. But what velocity do we use? All right, do we half the velocity? Do we take a percentage of the velocity? No. All right, that child is traveling at that velocity of the child and the bike. So we're just going to keep that one velocity. All right, so we have 21 times 4.5. We do get 94.5 kilogram meters per second, again to the northwest. And then last but not least, I want to find the individual momentum of just the bike. All right, so if I'm looking for the momentum of the bike, I'm going to use the bike's mass times the velocity of both of them. So that's going to be 5.9 times 4.5. So 5.9 times 4.5 does give us 26.55 kilogram meters per second to the northwest. All right, now what I want you to do is I want you to look at that green and that blue. All right, so the green is the child's momentum, the blue is the bike's momentum. All right, even though both of them have the same velocity, they do not have the same momentum. Their momenta are very different from each other. And that's because their masses are different. So it would be the same thing. If their masses were the same, All right, and their velocities were different. The one with the larger velocity would have the greater momentum, just like the one with the greater mass has the greater momentum here. All right, I want you to also look. If we were to add these two together, 94.5 plus 26.55, what does that give us? Do that in your calculator real quick. It gives us 121.05. What do we notice that is? It's the same as what we did in the first part. All right, so I could have done just step 2 and step 3 first and then just added them together to have gotten the total momentum third. All right, so that's just something that we need to keep in mind to think about. All right, now we looked at an example that was very similar to this in our energy unit. All right, I don't know if you remember it, but we did look at it. It was whenever we were trying to get the bowling ball and the ping pong ball to have the same amount of kinetic energy. All right, we wanted to know how fast the ping pong ball would have to be traveling in order to have the same kinetic energy as the bowling ball. All right, it was like 160 meters per second, which was a ridiculous amount. So no, it really wasn't feasible for that ping pong ball to have the same kinetic energy as that bowling ball. All right, but for this one today, we're not dealing with kinetic energy. All right, so today we have a pitcher who claims he can throw a 0.145 kilogram baseball with the same momentum as a speeding bullet. All right, I want to assume that the bullet has a mass of 3 grams and moves at a velocity of 1,500 meters per second. I want to know, what will the baseball speed be if the pitcher's claim is valid? All right, so we know that we want the momentum of the baseball to equal the momentum of the bullet. All right, the BB is baseball, the single B is bullet. So we know that we want our two momenta to be equal to each other. All right, we have our mass of our baseball. That was our first given, is 0.145 kilograms. Kilograms are exactly what our mass should be found in, so that's great. All right, we're then given the mass of the bullet, which is 3 grams. All right, big red flag should be thrown up in your head right now. Mass cannot be found in grams. So we divide it by 1,000 to get it to kilograms, and that is 0.003 kilograms. All right, so that's the mass of the baseball, and we know, or we're assuming, that the velocity of the baseball is 1,500 meters per second. Now, I don't tell you what direction this baseball is going, but we are just going to assume that it's going in that positive direction. And the last thing is what we're looking for. It says, what must the baseball speed be if the pitcher's claim is valid? All right, so we want to find the velocity of the baseball. All right, well, in order for us, given everything that we know, we have to find the momentum of the the momentum of the bullet first. All right, so we know that the momentum of the bullet is equal to the bullet's mass times its velocity. We have both of those. So it's going to be 0.003 times 1,500. That's going to give us a momentum of 4.5 kilogram meters per second. And if our velocity was assumed to be positive, our momentum will also be positive. Well, we know that the momentum of our bullet is equal to the momentum of our baseball. All right, so we know the momentum of our baseball is equal to the baseball's mass times its velocity, and we know we're solving for that velocity. So to get rid of mass that's being multiplied, we are going to divide that mass on both sides. Again, the BB is baseball. All right, so the velocity of the baseball is equal to the baseball's momentum divided by its mass. So that's going to be 4.5, divided by 0.145. And we should get 31.03. 31.03. All right, we are solving for velocity that's measured in meters per second, and it's going to be plus. Now, if we were to turn this into miles per hour, that's a little under 70 miles per hour. So, yeah, it's totally feasible for that pitcher to have to pitch a ball with the same momentum as the speeding bullet. All right, so we just proved that right there. All right, so I hope that all of this is okay with you. This is just looking at momentum itself. All right, but before we move on to this next thing, I want to remind you of another theorem. All right, so we're saying theorem right here. All right, we had another theorem in our last unit. All right, so we talked about how if there was any change in energy, all right, it didn't matter if it was kinetic energy, gravitational potential energy, or elastic potential energy. All right, all of those changes in energy were due to some kind of work having been done. All right, whenever we did our power lab, whenever you were running up the bleachers, at the bottom of those stairs, you did not have any gravitational potential energy. At the top of those stairs, you did. But what did you have to do in order to get to the top of those stairs? You had to put in work. You had to apply a force, which was your weight, and go a distance, all right, the distance, the height of the stairs. All right, so we saw that a change in that energy was caused by work being done. All right, well, this time we're not looking at energy, we're not looking at work, we're looking at momentum. All right, so if I have a change in momentum, that probably means that I have something that's changing its velocity. All right, so if we know that momentum is mass times velocity, if something is changing its momentum, it's probably changing the velocity. So we can start by breaking down that delta P. We know that delta P can be broken down into final minus initial. All right, and then we know that if it's mass times velocity, and velocity is the thing that is being changed, then our final momentum is going to be our mass times our final velocity minus our mass times our initial velocity. All right, so that's just breaking down that delta P. All right, that's that change in velocity. So if we ever see any kind of change in velocity, that should tell us that we have a change in momentum. Well, we know that a change in momentum has to be caused by something. All right, and if you think about it, if we're changing velocity, whether that's speeding up or slowing down, a force has probably been exerted over a certain amount of time, and that's exactly what's happening. All right, so this is something called impulse. All right, impulse is the product of the force and the time over which that force is acting on the object. All right, so impulse is actually signified with a capital J. This is not like a J for joules. Joules are a unit. This is an actual variable. Is equal to our force times our time interval. All right, so we know that because of this theorem, we know that our impulse is what is causing that change in momentum, which means that our impulse is equal to our change in momentum. All right, and if we sub in the force times time, that force times time is equal to our change in momentum. All right, so this is the equation that you will be given on your quizzes and your tests. The main thing that you have to know how to break down is this delta P. And again, delta anything can be broken down into final minus initial. And then we know that if it's momentum, it's going to be the velocity that's changing. So that's where that mv final minus mv initial comes from. All right, so this one is super important. All right, so this is the one that you will be given. All right, so let's look at a couple of cases. All right, this first case, say you are playing baseball. All right, most of the time you want that baseball to go as far and as fast as possible. If you are playing golf, most of the time you want it to go as far and as fast as possible. If you're playing tennis, you are going to want that ball to go far and fast. All right, so what we want is we want a huge change in momentum. All right, well, if we want a big change in momentum, if we know the impulse is what causes that, then we want to apply a very big force over a very long time interval. All right, so the way that we do that in those three scenarios, all right, if you're playing baseball, all right, you don't stop your swing as soon as the bat hits the ball. No, you're going to continue swinging all the way through. Same thing with golf. You don't, if you're trying to get it super far away, you don't just stop that golf club as soon as you hit the ball. All right, you're going to swing through. It's the same thing on a tennis court. All right, you are not going to just stop your racket as soon as it touches the ball. No, you are going to swing through. And swinging through is exerting that big force from the bat, from the golf club, from the racket for as long as possible. All right, so we want to follow all the way through, swing through, all right, so that we can extend the time that that force is being exerted. All right, another example. This one's my favorite. All right, so let's take these two vehicles right here. All right, these vehicles are going to have the same mass. All right, they're identical. I'm just going to throw a number out there. All right, that's definitely too small for a car, but it's fine. All right, so both of these cars have a mass of 150 kilograms, and we'll say that they are both going at 60 miles per hour. All right, so they're going pretty fast. All right, so say this car hits this brick wall. What is that final velocity going to be? All right, so it's going to bring it to a stop. So that final velocity is going to be 0 meters per second. All right, this car hits a ginormous amount of hay, all right, that eventually does bring it to a stop also. All right, so it has a final velocity of 0 as well. All right, if we have the same cars with the same masses, same initial velocities, and same final velocities, both of these scenarios have the same change in momentum. All right, if they have the same change in momentum, that means that they have the same impulse. All right, but what they are experiencing is different. All right, so I do want you to write that down. I want you to write it out in word form if you can. All right, these cars, because they have the same mass, same initial velocity, and same final velocity, they have the same change in momentum. And because they have the same change in momentum, that means that they have the same impulse. All right, so that means that this one, we'll call this J1 for the car that hit the brick wall, and this one J2. Numerically, J1 is equal to J2. Remember that impulse is signified with a capital J. That's why you see that J right there. All right, now, what is the difference between these two scenarios? All right, that car that hit the brick wall was brought to a stop in a very, very, very short amount of time, almost immediately. All right, so if we have a small amount of stop time, that means that our stop force is going to be so big. All right, so the force that this car experienced was so much bigger than the car that hit the hay is because its stop time was so small. The car that hit the hay brought it to a stop in a relatively large amount of time. So it had a long stop time, which made the stop force very small, relatively speaking. All right, so which barrier would you rather hit, the brick wall or the hay? All right, I'm definitely going to say the hay. All right, I want to extend that time, that stop time, as much as I can so that I can decrease that force, that stop force, as much as I can. All right, and this one is still kind of looking at that car hitting the brick. It's the same thing. All right, so if we want to decrease that momentum, so we want to bring it to a stop, slow it down, whatever, over a short amount of time, that means that the time that we are in contact or that force is in contact is very, very brief. All right, the time is very short, but that force is very, very large. All right, so this is the same thing as that car hitting the brick wall. All right, look at these examples. All right, so this swinging through is going to give us the greatest change in momentum. We have a really big force over a really big amount of time, which is going to give us a really big change in momentum. All right, so, and that's what you want most of the time whenever you are hitting a baseball, a golf ball, a tennis ball. All right, all of those things. So it's increasing the time that force is in contact, all right, which increases that change in momentum. All right, the rest of these are wanting to decrease the momentum. All right, so did you know that your car is actually made, it's designed to crumble? All right, so think about if you had this identical car, but it was not made to crumble. All right, so say you were going the same speed and you hit that wall. All right, if your car did not crumble, you would stop almost immediately. So you would have a very, 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 very short stop time, which means that your amount of stop force experienced would be through the roof. All right, and we don't want that. Whenever we're in a crash, we want to feel the least amount of force as possible. All right, so that's where these crumble zones come into play. All right, so whenever your car hits something, it is designed to crumble so that it extends the stop time, which decreases the stop force. It's the same thing with these eggs down here. All right, if these eggs are the same mass and they're being dropped from the same height, that means that their initial and final velocities are going to be equal as well. All right, so we're going to have the same, hang on, the initial one, the final one, the final two, okay? So because all of those are the same, that means that our change in momentum is again going to be the same, which means that the impulses are going to be the same for both of these. All right, what changes is that this egg, all right, you can see that two very different things happened as they came to a stop. All right, the difference is that this plate did not increase that stop time. It had a very, 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 very small stop time, which means that you had a very, very, very large stop force, which is why it cracked. All right, the pillow cushions or cradles that egg, so it extends the stop time. All right, so you have a big stop time, which decreases the stopping force, which is why that egg did not crush. all right, or did not crack or break open. All right, it's the same thing. So if you are ever getting punched, I guess, all right, hopefully you're not, all right, but if you ever get punched, all right, you do not want to tense your neck or tense your jaw muscles. All right, if you do that, you are going to make that fist stop in a very, very, very small amount of time. All right, which means that the amount of force that you are going to be feeling is going to be huge. All right, what you want to do is something called riding the punch. Riding the punch. So you want your face to go with the punch. So that increases the stop time of the punch, which decreases the amount of force that you are experiencing. All right, like I said, I hope you never get punched, but riding the punch is going to be that example of increasing the stop time so that we decrease the amount of stop force. All right, we're almost done. Let's look at this next practice. All right, so we have a 1,400 kilogram car moving westward with a velocity of 15 meters per second that unfortunately collides with a utility pole and is brought to rest in 0.3 seconds. I want to find the force that is exerted by that utility pole on the car during the collision. All right, so we have our mass of the car, that's 1,400 kilograms. All right, we're given our initial velocity of the car, which is 15 meters per second. I told you this car was traveling westward, so that is going to be a negative 15 meters per second. All right, and then we said that after it collides, it is brought to rest. So that tells us our V final is 0 meters per second. All right, it did so in 0.3 seconds. All right, I want to find the amount of force that was exerted on it. All right, now here we are looking at a change in velocity. This car was moving and then it stopped moving. All right, so there is a change in velocity, which means we have a change in momentum. And we know that a change in momentum is caused by an impulse. We know that impulse is equal to that force that has been exerted over the amount of time that it's been exerted. All right, and that's equal to our change in momentum. Now here, I'm looking for the force. So if I'm trying to solve for force, I need to divide time on both sides. So my force is equal to my change in momentum over my time. Now, I know that delta anything is final minus initial. So my change in momentum, delta P, is equal to my final momentum minus my initial momentum over my time interval. And I know that because P, momentum, is equal to mass times velocity, my mass is not changing here. Only my velocity is changing here. So we have mv final minus mv initial over time. All right, now our final velocity is 0, which means that this whole thing is 0. But I do not want you to just take that completely out of the equation. All right, this 0 comes first, so it's going to be 0 minus a number. All right, so we have 0 minus 1,400 times negative 15 all over our time interval of 0.3. Well, 14 times negative 15 gives us negative 21,000. So what is 0 minus a negative 21,000? It is a positive 21,000 divided by our time interval of 0.3 seconds. We divide 21,000 by 0.3. Our force is a plus 70,000 newtons. And that plus tells us that that force is going in the positive direction. It's going east. All right, we were told that our car was traveling west, all right, whenever it ran into the utility pole. So in order to bring that car to rest, that utility pole had to exert a force that was going in the opposite direction, which is east. Okay? Now, this is our last one. All right, I want you to solve this on your own. I'm going to give you the answer. All right, the answer is 4 seconds. All right, but I want you to work this out and solve it on your own. If you do not take everything into account, hint, hint, like direction, you will not get this answer. So what I want you to do is I want you to write down all of your givens. Look what's happening. Write down all your givens, write down your unknown, and I want you to solve for the time. It says, how long does it take the car to decelerate? So you're looking for the time. All right, your answer is 4 seconds, but I want to see how you got there. All right? All right, this is where we end today. As always, if you have any questions or need any help, you know where to find me. Bye, y'all.